Okay, thanks a lot. Can everyone hear me? Great. So the starting point of this talk will be program sensitivity. I just want to review that for a bit and then show what we do to generalize it to probabilistic programs and how we might verify such properties. So program sensitivity is a very well-studied property in verification and also mathematics before. And the idea in a nutshell is that similar outputs to a program should yield similar inputs to a program should yield similar outputs. Right? So if you're designing some program, maybe you want to make sure that it's not too sensitive to small changes in the input, because maybe there's a bit of error in the input or something like this. You don't want small changes in the input to lead to huge changes in the output. So in verification, this is often called robustness or continuity, and in mathematics, people often call it, say, Lipschitz continuity or contractivity. And a bit more formally, the idea is that a program or a function goes from inputs to outputs, and both on inputs and outputs, there's a metric, right? So there's a distance on inputs and a distance on outputs. For our purposes, the distance will just map pairs of elements to a positive real number. Won't use any other properties. And the guarantee we want is that for all pairs of inputs, in1 and in2, the distance between the corresponding outputs after running the program on these two inputs, this distance should be lesser than or equal to the distance between the inputs. Right? So if kind of the distance between the inputs on the right is small, then the distance between the outputs should be small as well. I just want to mention that this is a very nice property for various reasons. For verification, a key property of sensitivity is that it's compositional. So for programs or functions satisfying this inequality, I'm going to say that it's just sensitive. There's many different ways of calling this kind of property. But the point is that if P is sensitive and Q is also sensitive, then the composition of Q and P is also sensitive. Right? So this is a basic fact that kind of contractivity or sensitivity is preserved by composition. In the probabilistic world, which is where this talk will take place, things are slightly different. Again, we want similar inputs to lead to similar output distributions. So here, the program, the randomized program, maps, say, a single input to a distribution of outputs. So again, we can say we're given distances on the input and a distance on the output space, which is now distributions. And we want for all pairs of input values that the output distributions are kind of bounded distance apart. Okay? So that raises the question of like, what distance should we take on output distributions? So somehow intuitively, when we're working with non-probabilistic programs, standard programs or functions, these non-probabilistic spaces, there's many standard distances. You may take the distance on the real numbers, or the distance on pairs of real numbers, or maybe the Hamming distance on sets. These are kind of standard distances. But for distance on distributions, we have a lot of different choices. And it's also not clear, which distance should we take for the output distributions to ensure that we have good composition properties. So this is the subject of this talk. In our paper, we do three main things. We give a new coupling-based definition of probabilistic sensitivity with good composition properties. We show that this sensitivity can support a relational program logic, which we call EpRHL. So we can use this program logic to prove probabilistic sensitivity for probabilistic programs. And finally, we formalize several examples of properties, including stability and probabilistic convergence inside this logic. So during this talk, I'm going to talk mostly about the first point. I'll briefly talk a bit about the relational program logic, the second point, and I'll leave the third point to the paper. Before I get started, are there any questions? All right. So first of all, what is a good definition of probabilistic sensitivity? So to kind of motivate this, I'm going to give two examples of probabilistic sensitivity that are kind of different, and they model different features, but somehow we would like to cover both of them and even more definitions with a more generalized definition. So one possible definition is just to say that the two output distributions must be close kind of uniformly. This is a very strong notion. So a bit more formally, we can define a distance on distributions. Say we have distributions mu1 and mu2 over set A. And I'm going to define the distance to be this quantity here. So it's going to be k times this maximum, where I take this maximum over all subsets of outputs. So what this is saying is that for every event or every subset of possible outputs, the probability of this event, I want to look at the difference of the probability of this event under the two distributions. And I want to take the biggest possible difference. So this is kind of a uniform notion of distance on distributions. And it leads to a notion that I'll call k-uniform sensitivity. So kind of the point is that this parameter k kind of controls the strength of this sensitivity guarantee. When k is larger, kind of to achieve the same distance between distributions, the difference between probabilities, kind of the second term there, must be smaller. So when k is larger, k uniform sensitivity means that the distributions must be closer together for corresponding inputs. And like I said before, it's a strong guarantee in that kind of the probabilities are close for all sets of outputs. For any set of outputs, it must be almost the same probability under the two distributions. There's no averaging or anything going on. All right? So I'll briefly sketch one application of this notion of sensitivity, and the classical applications for proving probabilistic convergence. So in this setting, we often have a probabilistic program that is a loop, and we want to say that the loop kind of forgets its initial state in some sense. So if we start from maybe two different initial states and we run this loop for many, many iterations, we want to show that the distribution on outputs converges to kind of the same distribution. So where you start kind of doesn't matter. And this can be phrased in terms of this k uniform sensitivity, where we say that, all right, the number of iterations of this loop is t. For t iterations, we want to prove that it's k uniform sensitive for a larger and larger function k of t. Right? So intuitively, as t increases, the distributions must get closer and closer together. So, and the relation between these parameters k and t will describe how fast the convergence happens quantitatively. So this is like just a very sketch application of k uniform sensitivity for proving convergence. A different possible definition of sensitivity is what I'll call mean sensitivity. So here we're working with distributions. The outputs are real numbers or maybe some numeric value. And we want to say that the distance between two of these distributions is going to be defined to be the distance between the average values of the distributions times some parameter k. So intuitively, this leads to a notion of sensitivity that I'll call k-mean sensitivity. And again, as k gets larger, the sensitivity guarantee is stronger. It means that the averages of the output distributions should be closer together. But also point out this is a weaker guarantee than uniform sensitivity. So it just says the averages must be close. It doesn't say anything about the probabilities of all the events or the probabilities of every single possible output. So this is yet another notion of sensitivity that looks kind of different from the one I showed before, but is still important. And the main application for this kind of sensitivity is for proving stability in machine learning. So to kind of sketch this setting, in machine learning, we might have an algorithm which I'll call A, and it takes as input a set of training examples, a set S, and it's going to output a list of numeric parameters. So it's going to learn some parameters about the world, something, given some training examples. And in many situations, this learning algorithm itself might be randomized, maybe for performance reasons or for regularization. But a typical danger of machine learning algorithms or a typical fear is that it overfits the data set. What does that mean? It means that the output parameters that the learning algorithm produces depend too much on the training examples. Right? So maybe on the training set, this algorithm produces parameters that get very, very low error, that predict very well. But when you start showing kind of new examples that you have not seen before, the parameters perform very poorly. So this is a bad feature of machine learning algorithm. We want to avoid this. And there's many ways to avoid overfitting. But one way is based on stability. So the idea is that if we consider a function L that maps the training set S to the average error of the machine learning algorithm on input S, which is, say, a real number, then if this average error is kind of similar for similar training sets, then it means that kind of the underlying learning algorithm doesn't depend too much on any particular input, and therefore it will not overfit too much. So we can formalize this, but this is the intuitive idea. And again, this can be phrased as an example of k-mean sensitivity. So kind of this function L that maps training set to average error of the parameters, this should be mean sensitive, or maybe k-mean sensitive, where I'm leaving off the quantitative parameters. All right, so are there any questions about these two kind of brief applications so far? Yes?
Why just a single example?
Sorry?
Why just a single example here?
Why just a single example here? So this is just, this is based on definition that was already present. I think, yes. So you can make it depend on two examples or things like this, but the original definition was phrased in terms of a single example. So we did not give this definition, actually. This is due to Lisov and Bousquet. But yes, they phrase in terms of a difference in a single example. Any other questions? All right. So these are two definitions of probabilistic sensitivity. There are others. So what we want is kind of a general definition that is expressive, so at least encompasses both of these definitions before, and has room to kind of characterize other kinds of sensitivity. And we also want it to be easy to reason about. So that can mean a lot of things, but for my purposes, I just want a definition that is compositional. So that satisfies compositional properties like that we have for the deterministic case. Right? And to do this, we're going to combine two ingredients to define a general notion of probabilistic sensitivity. And this is based on the idea of probabilistic couplings. So the first ingredient is probabilistic couplings, and intuitively, a coupling is a single distribution that models two distributions. Right? So I have two distributions, here the output distributions, and I want to model both of these distributions with a single distribution on pairs. So given two distributions, mu1 and mu2, a joint distribution mu, which is over pairs, is a coupling if the first marginal of mu is equal to mu1 and the second marginal of mu is equal to mu2. I won't go too much into the motivation of this, but I'll just say that this is kind of a well-studied notion in probability theory and has also been receiving more interest in formal verification recently. And that's because of this typical pattern, which is that to prove a property about the two distributions, say two output distributions of your program, it suffices to construct a coupling of the two distributions with certain properties. So if I want to prove some complex relational properties of two distributions, all I have to do is construct or show that there exists a coupling of these two distributions with certain properties. And for various reasons, this can be often easier to do than to prove their property directly. So this is the first ingredient. The second ingredient is that we're going to have a lifting construction on distances. So idea is that we have a distance on kind of samples, or kind of the ground set, and we want to lift this distance to a distance on distributions over the ground set. Right? So say we're given two distributions, mu1 and mu2, over set A, and we're given a ground distance on the set A. So this distance you can think of as kind of non-probabilistic. It doesn't talk about probabilities or expected values or anything like that. All it talks about is how to map every two samples to a real number, say a positive real number. And we want to construct from this distance a distance on pairs of distributions. So this is the full definition here, and I'll try to walk through this slowly. It looks rather mysterious, but we wanted to define a distance which we call d sharp or d lifted on pairs of distributions, mu1 and mu2. And the idea is that we're going to take a minimum here over this set C, and the set C is the set of all couplings of mu1 and mu2. So mu on the left is a distribution over pairs, and we're taking the minimum of this average value of the distance, the ground distance d over this coupling. So this likely looks very mysterious, and I can't quite say exactly like why this is like a very good idea at this point, but I'll just want to say that this supports kind of there's a kind of an analogy with the previous definition of probabilistic couplings, which is that if we want to bound this distance here on distributions, it suffices to construct the coupling between the two distributions mu1 and mu2, where the average distance d is small. Right? So kind of if we want to prove a property, again, a property about two distributions, or we want to bound a distance between the two distributions, it suffices to construct a coupling with certain properties again. That's the overall big picture. And given this definition, we can now define probabilistic sensitivity. So we have a function f from a set A to distribution over B, which we could think about as a probabilistic program or a randomized algorithm. And we're given distances d in and d out over the sets A and B. So both of these distances are again over the ground set. They don't talk about distributions or probabilities. And we just want to say that f is going to be d in, d out expected sensitive if this holds. Right? So it's just like a definition of sensitivity we saw before, except that the distance on distributions, on output distributions, is this lifted distance on the left. So kind of for every pair of inputs, A1 and A2, the lifted distance between the output distributions is at most the distance between the inputs. So this will be the definition of expected sensitivity. And going back to our motivation, I said we wanted a general definition that is expressive and also easy to reason about. So for expressivity, it's possible to show that by varying the distance on output, the ground distance, we can recover some of the notions we saw before. So for instance, if the ground distance satisfies this property, where for every pair of distinct elements of distinct output, the distance is at least k, then d in, d out expected sensitivity implies k uniform sensitivity. And likewise, if the outputs are real valued and we take kind of the distance on the ground distance on outputs to be just the normal distance on real numbers, then D in, D out expected sensitivity implies K-mean sensitivity. And by varying kind of the ground distance, we can recover other kinds of sensitivity. For easy to reason about, expected sensitivity satisfies a nice composition property. So if I have a function f that is randomized and from A to a distribution B, and it's dA dB expected sensitivity, and a function g from B to distribution over C, which is dB dC expected sensitive, then kind of the composition, the Claise composition, the probabilistic composition of these two functions is also dA dC expected sensitive. Right, so what's nice about this kind of property is that when analyzing composition, I never have to think about distributions or probabilities. So I've abstracted away from expected values or kind of these more complex details about the distributions. You can view this as kind of a monadic composition principle. Right, so briefly in my remaining time, I'm going to talk about how to verify this property. I just want to give a very brief glimpse of this logic that we developed called EpRHL. It stands for Expected Probabilistic Relational Hoare Logic. It's based on various probabilistic relational Hoare logics. The basic language is this basic imperative language where you have assignments, conditionals, loops, skip, and also sequencing. And the new command is a sampling command. It samples from D and stores it into X. And the judgments of this logic look like the following form. So it looks quite like Hoare logic or standard program logics, where you have some kind of precondition and you have some programs and you have a postcondition. So since it's a relational program logic, we're relating two programs. So there's C1 and C2. And generally, P plays a role of a precondition. So it's a Boolean predicate over kind of pairs of memories. And Q is also a Boolean predicate over pairs of program memories. And it's also the kind of the postcondition. And now we also have kind of a pre-distance and a post-distance. So D in and D out. And they're again real value expressions over pairs of memories. So the things inside braces are not talking about probabilities. And the point is that the interpretation of this judgment corresponds to expected sensitivity. So this judgment is valid if kind of for all pairs of memories satisfying the precondition, then there exists a coupling of the two output distributions such that the support is inside Q and also the expected value of the output distance is at most the distance between the pair of inputs. So it's going quite fast because I'm running out of time, but there's a close correspondence between these judgments and expected sensitivity. I'll just show one proof rule, which is the rule for sequential composition. So if you kind of squint, you can see this is sort of like the normal rule for sequential composition from Hoare logic, just with more components. So we have the first judgment relates C1 and C2, and the second judgment relates C1 prime and C2 prime. And we want to relate C1 followed by C1 prime to C2 followed by C2 prime in the conclusion. And I just want to point out that the distance is composed in the way they would expect, right? So the first kind of judgment means that roughly the first thing is dA dB expected sensitive. The second judgment means that it's dB dC expected sensitive. And in the conclusion, kind of the composition is dA dC expected sensitive. So it composes as you would expect. All right, so just wrapping up. There's plenty more in the paper, so we have more theoretical results like the full proof system for sampling, commands, conditionals, loops, etc. We also have a very interesting transitivity principle that internalizes what's called the path coupling principle. So this is investigated by people in probability theory, maybe in the 1970s. We also have an implementation of the logic in EasyCrypt and formalizations of various properties of probabilistic programs. And looking forward, there's several possible directions. So first of all, there are kind of other useful consequences of expected sensitivity. So I showed two. But by varying the ground distance, we can recover other kinds of probabilistic sensitivity. Another question is whether we can use this technology in formal verification systems beyond program logics, right? So kind of the general idea of expected sensitivity isn't tied to program logics. We would hope that we can use it in other settings as well. And finally, how can we automate this proof technique? So we've abstracted away a lot of the details. So hopefully we can make this technique more automatic, but it remains to be seen. And I just want to finish by making a shameless plug that I'll be starting at Wisconsin in the fall, and I'm looking for students. So if this is interesting to you, let me know. And that's all. Thanks. Uh-oh. Uh-oh.
So, in a machine learning community, as far as I understand, there are many distances in between probabilistic distribution. For example, Carback, Library, or cross-entropy. What is the difficulty in those well-known
Yes, that's a very good question. So there are indeed many different distance zone distributions, like Hale divergence or Hellinger distance, or various distances associated with differential privacy. So the difficulty in using, so this kind of technology or these ideas here support a class of distance zone distributions, but not all distance zone distributions. I think for me, the main difficulty is showing composition, right? So we want to show that composition result holds, and for Hale divergence or other kinds of more complex divergences, it may not be true, right? So to give modular verification, try to simplify the verification, we want to strike a balance between expressivity and kind of composition. So composition is like a very key, I guess, principle, I guess, or motivating idea behind this.
Okay, thank you. Okay, hi. So,
Hello.
Manchan from CMU. So, I
Hi.
have a couple of questions. So, the first one is, can you reason about the Theobald property of sensitivity? So, that means that you can compute reason about what is the property such that a program is sensitive.
That's a good question. So, are you saying like a property like with high probability it is low sensitivity?
Right.
Yes, that's a quite good question. I do not know. I do not know.
So the second question is, do you think that we can apply the concept of the sensitivity to the side channel attacks?
The side channel attacks.
Yeah, because
that's a good question as well, right?
Yeah.
So what I presented is kind of just a mathematical abstraction, I guess. So a lot of these ideas are just using like functions from mathematics, so there's no concept of side channel. You would have to kind of incorporate that somehow inside the model. So maybe we can maybe perhaps model the side channel as somehow another output that is not the output that you actually care about, but maybe like how much energy is used or how long something takes. But I don't know. That's a good question as well.
Yeah. Okay, nice.
Hi. The distance over the inputs, that's just a function over the inputs, right? Can you generalize, weaken, or lift to distributions over inputs?
That's a good question as well. So certainly you can generalize to distributions over inputs by just lifting the distances before. But let me see.
Does the soundness hold?
So I'm not sure about that off the top of my head. Typically, I've been thinking about the inputs just being deterministic. So there's no need to lift the distance on inputs to distance on distributions over inputs. But if you consider another kind of reasoning, maybe it's better to view the programs as mapping distributions to distributions, and then you would really want to work with distributions on inputs as well. I'm not sure whether this will make it easier or harder. It's a bit hard to say.